Good morning. Thank you, Wolfgang. My name's Dave Hughes. Thank you for the introduction. I'm the CEO and founder of Hcc Embedded. And today I'd like to talk to you about all the high-level issues that you need to think about when designing an embedded file system for your project, how you're going to use storage on your embedded project. File systems are critical to many projects. Historically, there's been some very well-publicized disasters like the Mars rover project. More recently, even the last week or so, we've had the Tesla announcement that they've got trouble with their NAND flash storage on their older models of cars, and as time goes by, will probably cause problems later. So flash management is critical and thinking about how the design works, and so we're going to talk about all the issues relating to file systems, flash management, and the things you need to consider in your design. So first, I'll just give you a very quick introduction to Hcc Embedded and what we do. We've been developing deeply embedded software since 2002. Our very first product was a fail-safe file system. We looked at the market back in those days. We saw people using standard file systems on NOR flash, fat file systems, and we're quite concerned about the fact that these devices would not survive an unexpected reset, a crash, a watchdog timeout. The file system would come back and be corrupt. And we wanted to provide better solutions for storing files to NOR flash, later NAND flash, and we moved forward. Obviously, it's a very, very dynamic market, and we've worked our way through all the flash devices and different storage media over the last 17, 18 years and continue to move forward with the different medias. Aside from that, we've also developed a lot of flash management software, networking and security software, and USB software. We have a total focus on quality, which is something we continuously work on and develop. We're ISO 9001 and 27000 certified. Over the years, we've built over 2,000 customer projects across all industries, geographies, all over the world, very different environments indeed. And our preferred method of delivering anything to our customer is as working projects on either customer hardware, on agreed development boards, but to actually show the technology working and having a common platform to debug and understand issues. And this is particularly interesting with things like file systems where you want to prove fail safety, you want to prove reliability, you want to prove wear leveling. So that is our primary focus. Back when we started, NAND flash, the largest NAND flash on the market was about a 32 megabyte chip with a 1-bit ECC requirement. That means you need to correct 1 bit per every 512 bytes to make that device stable. Now we've got to a point where the biggest chips are now about 128 gigabyte with maybe 40 bits of ECC for 512 bytes data. Moore's law is really well challenged by flash technology, the storage technologies that underpin everything, your SSDs, your SD cards, USB. This is why you have to keep very much your finger on the market and understand what's going on and all the issues, and also make designs that are appropriate for what you're trying to do. So we're totally focused today on file systems and media connectivity and the problems that you have. Over these last 17 years, 18 years. This is a simplified diagram of how we connect all our file systems, the different connection possibilities, how you connect different media and to different interfaces and how hosts can communicate with it. Central to the embedded system is a common file system API, which we interface to the different file systems. Below that, there's different media types, and there's a standard file system driver interface below which we can support standard media like SD card, eMMC, USB mass storage, etc. And then on the high level side, there's you can externally interface to the embedded system and read the file system either through USB and mass storage or through MTP or through FTP or other proprietary means. So this is quite a complex scenario. We now have 8 file systems, 2 flash management layers. You might wonder how on earth we got into such a mess. Why is all of this stuff necessary? Somebody sitting in a business school would probably come and give us a lecture on we really should optimize our product portfolio. But actually, that's not how we see it. We see all these products as important. They're all part of the story of how we can provide the right solution to the actual problem being faced. Why are things so complicated? Why do we need so many file systems? Well, for some people in deeply embedded space, 64K is lots and lots of RAM. For other people, 32 megabytes, they say to us, oh, I've only got a small amount of RAM, just got 32 megabytes. Embedded systems just are extremely varied. The available resources, there are cost restrictions, the variety of MCUs. When we started developing file systems, things like the 8051 was very common, 8-bit microcontroller. Then we had things like the MSP430, 16 bits. Now you have a huge range of 32-bit microcontrollers, many of which are ARM-based, but many more. The variety of media types, we've mentioned the variety of the changes in the flash technology over the last 18 years. This continues apace. We've gone through SLC NAND, MLC NAND, now we've got TLC NAND, and on we go. The technology keeps changing, and that gives very different media types that we can use. On top of that, you've got the variety of interfaces. On some systems, you use full bus interfaces to a parallel NOR flash. Others, you use SPI interfaces to a NAND flash. Otherwise, you used to have 1-bit SPI interfaces to MMC cards. Now you have 8-bit interfaces to octal interfaces to SPI. And on top of that, you have the variety of applications. And Hcc have, in their 2,000 odd projects that we've developed for customers, supplied to all sorts of environments, which really had such different requirements that one file system doesn't fit all. In fact, we need 8 file systems to fit all and 2 translation layers. We have file systems mounted on drill bits at the bottom of the North Sea. A disaster if you pull that up and discover you've lost all your data when something has happened and you needed to record it. We've also got file systems being installed on the next space shuttle. Again, very important in terms of making sure that that system works, but a completely different environment to the bottom of the North Sea. We've had other specialist environments like having it tied around bears' necks in Canada so that they can track bears for 6 months, and when they come back, they take the card off them and find out where they've been and what they've been doing. Something that requires a different approach because it's all battery driven, but you need to make sure that it's reliable because if you lose that data after 6 months, it's very painful. And the variety of applications is really weird and wonderful that we've got involved in, and indeed fascinating. But it's also the motivation for having all these file systems and options. So now what I'm going to try and do today is to explore the different issues that drive you to choose one solution or another solution when you're building an embedded system. So first, I think it's important to try and understand what a file system is trying to do for you. A file system is a way of creating a standard interface to a user application such that it does not have to understand the media. It can simply open a file, write to that file, read from that file, do whatever manipulation, close that file, and it assumes that the system below handles everything and it has no effect on the user application. This is never completely true in practice. The two things that affect user applications in this respect that you can't do anything about and you need to factor into your design. Firstly is the actual speed of the physical media and the media drivers. You will have huge differences in speed, several orders of magnitude between your slowest NOR flash interface and your fastest SSD interface. And that, of course, affects the timing of your application. And the other factor that you can't get away from is the fact that if you've got multiple user applications accessing the same drive, inevitably the file system will cause delays between the two if they're both trying to access it at the same time. But from a pure writing a piece of C application code or similar, The API is the same, the way it's managed is the same, but these factors have to be considered once you get down to the real world of actually using a device. So now once we've established that this is what we want to do, we want to create this abstract interface, we then need to think about, well, what are the parameters that are going to drive my choice of file system? What are the things that are important to us? And here I've tried to list the main factors, high level, and then these will generate more detailed factors that you need to consider in your design when you're trying to build an embedded system that's reliable and meets your requirements. And the first factor is, do you require a removable media, like an SD card, an MMC card, USB stick? Second factor is going to be whether it needs some level of external compatibility. So does that need to be readable by a file system on a PC? Or is the data always going to be read locally? So can you just use a proprietary file system that uses just a local file API, and you have no need to have that readable by some other alien system? The next factor is your available resource, your ROM, your RAM, your CPU speed, etc. These are also often linked to the cost of the system, because obviously if you're trying to do a low-cost solution, you'll probably end up with a slower MCU with less ROM, less RAM. So this is a major design consideration, and also related to that is the actual physical interfaces available for talking to your media. The next is the size of the storage media required. Now, how much data do you need to store? For how long do you need to store it? This is obviously very application dependent and needs to be assessed. Just simply blindly choosing the largest you can take will create unnecessary expense and also complexity. I mean, in general, the largest is an SSD these days, but it's not really suitable for an embedded system. So typically, you want to try and find the right balance between your data requirements and an easy, convenient way to manage the media. The type of storage media that relates back to the size, relates back to the removability of it, and relates back to the interfaces. Another key area is the performance. Obviously, every embedded application, when you're trying to design it, you need to think about what the performance is required of that. Do I need heavy read performance? Like if I'm booting, I might want to be able to read very quickly a boot image so that I can get a good boot up time. Or I may need to be able to display graphics files or something within a certain time. It all depends on what your application really requires of the file system. Equally, my write speed. Many systems don't really need high write speed. If you're doing a meter reading every hour, every day, even if it's a few K, that's a very low write performance. But if you're trying to record video data to a file, then you need a completely different level of write performance. So that is obviously a very key factor in your assessment of the system and the choice of media and file system. And the third major performance issue is endurance. How long do you need the data to be reliable for? Different media are reliable in different ways, but if you keep writing to flash over and over again, it will wear out. That is a fundamental point of flash, and it doesn't matter whether it's embedded in an SD card or eMMC, whatever your media, flash will wear out. So one of your design considerations you need to think about when you're designing your system is how long does this data need to be available and stable for? Clearly, when we put a file system on a drill bit at the bottom of the North Sea, we know that's going to be pulled up every 6 months. So we only need to design with the idea that the data is going to last a year or two. Other environments we get into where we get involved with, say, contracts with major meter manufacturers, they have legal requirements to make the data valid for 15 years. That requires a completely different design approach to if you've just got a requirement to last for 6 months. And you can obviously make optimizations appropriate to your design by doing this. And the last, and for Hcc, one of the most important factors in your design considerations is fail-safe important to you? Is it important that if my system accidentally resets, if its power is lost, and is it important that the file system comes back in a safe state? Most people would probably instinctively say yes to that question, but in some cases it's not that critical. It's just some logging data that's not important. But if the answer to that question is yes, then you need to think very carefully about your the file system, your choice of file system, choice of system. And we'll go into more detail on the issues of fail safety later. But from your standard file systems available on the market, particularly things like you can download from the silicon vendors, the things that come with standard packages, generally they do not provide any level of fail safety. And if they do, there's a few caveats which we'll discuss later on. So we often, as a company, we often get customers come and ask us and say, how fast is your file system? This question is really unpleasant for us to answer. There are just so many configurations, so many different variables, the cost, the performance, the data usage. Answering that question, we will always say, well, you know, in any particular environment, we will get the best out of it, but we can't, but giving it a raw number without the detailed information is a bad approach. What you should be doing is trying to define your requirements, analyze your application, decide from all those things we just discussed in the last slide, what is important to you, and then make a design based on that, and then try and make sure that you can meet the requirements in terms of performance and speed, endurance, read speed, write speed, endurance. I like to misquote a former British Prime Minister, a very 19th century British Prime Minister, Benjamin Disraeli, who was often quoted by Mark Twain, who used to say that there are lies, damn lies, and statistics when he was particularly frustrated with the economic numbers, I think it was at the time. For us, we see that there are lies, damn lies, and benchmarks. When applying, benchmarks are often generated for file systems, but in reality, the benchmark you're interested in is the one that applies to your application of the flash, the file system in your environment. And it is very unlikely that standard benchmarks will particularly apply. I have one very educational benchmark that Hcc generated many years ago on an MSP 430, where we managed to create an extremely, relatively fast writes to an SD card using an MSP 430, writing data from RAM using DMA, and achieving some speed. I think it was on an 8 megahertz processor and maybe getting 50 kilobytes per second, which is quite a low speed by today's microcontroller standards, but for that time processor was actually a good performance. But the thing about that was that it would only run if you could do continuous DMA. At that speed, it would only run if you could do continuous DMA. But if you've got a real embedded system, you need to be collecting data from somewhere. Otherwise, there is no point to the process. As soon as on that microcontroller you collected data, that would disturb the DMA and the performance would drop massively. It would have a huge effect on the overall performance. So although the benchmark was a lovely engineering project, came out with a really nice number, it was actually practically useless because you couldn't ever use those benchmark numbers in a real world application. So I can only emphasize, and this is also something we get from doing safety type development, it's important to define your requirements, what you need from your system, and then match it with the right media, the right file system, and build your applications with all this known. Another very important thing about this is that Flash is relatively easy to model. So if you know what your project is going to be doing, if you know how you're going to be writing data over the next 15 years, then you can model that and see how the flash gets worn, what the speed of it's going to be at various points in time. All these things are very reasonable to analyze. I won't say easy, but certainly not difficult to analyze exactly the type of behavior you will get from your flash based on your application. So let's now start exploring some of these issues of how we make choices in the file system we use. First is, let's look at external connectivity. So one standard method of accessing a flash medium is using USB mass storage. So this diagram shows the PC connecting to a USB device interface through mass storage, and it connects directly to the file system driver interface and writes to an SD card or a USB stick, depending on what the system, what is on the embedded system here. In this particular instance, the PC is directly controlling the media, and this means that you have to cut off the file system locally, because if the local file system that's also using the system standard file system driver interface modifies sectors, then you're in kind of blue screen territory. You're going to confuse the PC, you're going to confuse the embedded system, because neither can see what the other one's doing. They're both modifying the physical media without knowing what's going on the other one. This is why many cameras, video recorders and things switch off locally when you plug them into the USB, because they're running standard mass storage interface, and they don't want the possibility that you can crash the PC or crash the local file system, because you modify some key fact entries in both systems at the same time, and they conflict. So the USB mass storage solution is good if you can switch off locally. It's very fast and efficient, but it does mean that you have to switch off locally and reinitialize on each side every time you make a switch between PC, local file system, PC, local file system. Each time you make that switch, you've got to reinitialize to see what the new state of the fact tables are, or whatever file system you're using on there. The alternative approach for external connectivity is to have an API-like interface to the file system, and the external device just becomes a task using the file system like any other excuse me, any other device on the embedded system. So this can be done through MTP over USB, and most phones are now enabled with MTP and camcorders, etc. Or you can also do it through something like FTP, so connect through TCP/IP and FTP. And again, the PC becomes a task using the file system like any other task on the embedded system. The other advantage of that is this means that the embedded system has complete control over the media. So all the reading and writing is done by the file system. So the PC can call, or the external system can call, open file, read file, write file. The file system manages it all, and therefore you can run things in parallel. Because Hcc file systems support simultaneous read and write to the same file, you can even get to a situation where a PC can read from a file that's been updated by sensor data being written to the file in real time. You can actually do the simultaneous access. So the big advantage of using an FTP type interface solution, i.e. the PC uses a file API over a network type interface, is that the embedded system remains in control of the media and all the access to it. It also means you can use any file system you want on the embedded side. So that means you can make a choice to use a fail-safe file system instead of the default, which is to use a FAT file system, which is unlikely to be fail-safe in any normal usage. So this is the one big design decision, quite straightforward, how you're going to make external connectivity to your file system. The next big design decision is your media type. There are probably hundreds of different options for connecting media to embedded systems, but the main 5 that we see in deeply embedded systems are listed here in this table. I've tried to summarize them in very general terms of what the differences are. There's the standard SDMMC card solution. There are many of these. They're removable, obviously. They're cheap. They're very high speed. But cheap, high speed, obviously, doesn't map to highly reliable or fail-safe. To make an SD card fail-safe, you have to choose a very special SD card that is more expensive than a standard SD card. If you go down your local shop and buy your SD card, your electronic supplier, 99% of SD cards are not designed to be reliable. They're designed for cost, speed, and cost per bit. They don't advertise that they're not reliable, But there are endless stories of people losing their wedding photos, etc., because the device reset at the wrong moment, battery failed at the wrong moment, whatever. These cards simply aren't designed to be fail-safe unless you pay a substantial premium and buy very specialist cards, of which there are a few on the market. You can then start to think about building a fail-safe system. USB drives, well, these are ubiquitous, they're everywhere, they're given away all over the place as marketing tools. You get them everywhere. They are removable, of course, pretty low cost, high speed. Big problem is that, as far as we're aware, there's no USB drives that show a capacity to guarantee fail safety. The USB drives is complicated by the fact that it has to go through a complex USB host controller to manage transfers. To make this whole system fail-safe, you're going to have to work out both the controller being fail-safe and the actual device itself. As far as we're aware, this isn't actually possible. So from our point of view, if you're looking for real fail-safe storage, USB drives is probably not the way to go. eMMC, well, this is basically an MMC card on a chip that you solder into your device. It's no longer removable, but it can be made fail-safe. It's designed to have, it's got commands built into it, which if you use them correctly, you can do reliable write from them, which means to them, sorry, you can do reliable write to them. Of course, there's added cost. This is not focused on the low cost, and the speed varies between medium to quite high. There are penalties to be paid. If you're going to write to it reliably, it's not going to be as fast as if you write to it unreliably. So there are speed penalties, as always. In all these things, there's no such thing as a free lunch. So you have to pay with something if you gain something. This is the way of pretty well all embedded development. Then there's the two basic flash types. There's NOR flash, which comes in two basic forms, parallel and serial. Obviously, that's not removable, but it can be made fail-safe with the right supporting software and the right hardware design. It's relatively high cost, but you tend to use it in relatively small devices. So typically, a lot of NOR flashes are down to sub-megabyte level, up to maybe 256 megabytes. There are larger ones, but most times you use NOR flashes in those kind of ranges. So the cost per bit, while being high, the actual cost tends to be not that high, simply because you don't buy them in such large storage devices. And the speed is relatively low, and that tends to be gated by the erase speed of the devices. Many NOR flashes, even serial NOR nowadays with Octal SPI interfaces, can do extremely fast read speeds, but the write speed is always gated effectively by the erase time. And the erase times on NOR flashes tend to be maybe 30-40 milliseconds for one block, which might be 64K, compared to something like a NAND flash, which all erasers tend to be sub 10 milliseconds for a much larger block of data. There are several orders of magnitude difference in the erase speed, which is the gating factor on the NOR flash. And then there's the NAND flash, which is obviously not removable, can be made fail-safe. There's an added software complexity with NAND flash because NAND flash has very special characteristics. It has bad blocks built into it, but in different places in each device. And it has bad blocks developed. And to maintain NAND flash to be stable, you have to have a Hcc, error correcting code mechanism, to make sure that if bits get corrupted, you can put them back to their correct state. So the software complexity is higher. The cost per bit is back down low again, and the speed is medium to high. Because of the need for error correcting codes and the management of the bad blocks, etc., the speed is very much dependent on the interface, the controller you use to control the NAND flash in your MCU. So in some systems, it can be quite slow if you have to do everything in software and manage it. If you have a level of hardware support, the speed can be extremely fast managing a NAND flash. So the next big design question to ask yourself, well, if I'm going to use NOR NAND flash, do I need a flash translation layer? What is a flash translation layer? The flash translation layer has the job of making a NOR or a NAND flash look like a set of sectors, 1 to max sectors. So that the file system sees just a media driver which has an array of sectors, 1 to max sectors, which are then physically, logically remapped to different physical areas on the actual flash. And the purpose of doing this remapping is twofold. The first is to be able to map out bad blocks, both manufactured bad blocks and bad blocks that develop. And the second reason for doing this remapping is to be able to wear level the flash so that you can use the flash evenly. Because the flash blocks wear out, the more you write to them, the more you erase them, the shorter will be their endurance. But if you can spread the load over the whole device, then you will increase your endurance. So when do I need a flash translation layer? Well, basically you need a flash translation layer if you're going to use a standard file system where you need to have good wear leveling, like you need long endurance, and if you and to map out bad blocks. There are special cases though, which our safe flash file system maps directly to the flash, which eliminate the need for flash translation there because we map directly into the flash and manage the wear leveling at a file system level. This simplifies things from a file system point of view and a complexity point of view. The downside to it is that it becomes non-FAT compatible. It's a proprietary solution. So if you're in a closed system, maybe with an MTP or FTP interface, Safe Flash can provide a very good solution for managing flash. But if you want a truly open solution where an external devices can access your NOR or NAND flash, then you're probably going to need to use a flash translation layer to manage your NOR and your NAND flash. And now we come on to HCC's favorite topic. I mean, this is the thing that we built our company on, was making fail-safe file systems for flash. The Safe Flash file system, which we first released in 2002, I think had one major upgrade in 2004-05, is still a stable, ongoing product and a core part of our product portfolio. But fail safety cannot be the property of a file system on its own. No file system can guarantee fail safety in isolation. If the media does weird things, it doesn't matter how good your file system is going to be, it's not going to make it fail safe. If your user application doesn't understand what fail safety means from the file system, then it's not going to get the right result out of the file system. So the message here is that you have to take a system level approach to file system design. Every layer has to understand what every other layer is going to give it in terms of the reliability and the quality of service you can expect from that. So for example, this table shows basically how Hcc constructs fail safety in a system. We tell the user applications that every file will be atomically changed from one state to the next state. And then every file will always be consistent. So if you do some writes to a file, until you commit it either with a close or a flush, it'll still be in its previous state. And then we'll atomically, if you do that, then we'll atomically switch the state. And this is done, this is the expected quality of service we give to a user application from our file systems if they're designed fail-safe. And then the file system then knows it needs to provide that level of service to the user application, but it can only do it if the media driver gives it a level of service that it can understand. And the requirements of all our file systems is that it expects data to be written sequentially and atomically updated, and that write errors are reported. Now these may sound like very basic things that ought to be in every media driver, but unfortunately they're not. If you look at how a standard SD card works with multiple dies and data being written in parallel, you cannot guarantee the sequence in which sectors are written to the media. And so if they get switched off unexpectedly, you could get a jumbled sequence. You might have two sectors not written, the next two sectors written, the next two sectors not written. There's no file system logic that will ever save you from this problem. unless you have some kind of RAID array that's separately looking after this, there's no way that you can produce logic that can deal with a random series of written and non-written sectors. And equally, we need to know if a write has failed, so either because the power has gone or there's an error on it. So if we write something and we're not told that it fails, then of course we carry on. At some point in time, that's going to cause problems later on, and there's nothing we can do about it. So having a correct media driver is really important to the system. So the file system has to be given by the media driver a level of service. And the media driver itself needs to be able to atomically update and commit sectors to the media. If it can't do that, then it can't guarantee a level of service to the file system. So all these things are very deeply linked. To give you a concrete example of where this kind of goes wrong is that if you look at Linux systems, there's about at least four file systems that claim to be fail-safe. And lots of people who find that when using these file systems, they don't actually achieve fail safety. And one of the problems here is that in Linux systems, often you have people who develop board support packages who write things like NAND drivers with no idea what version of Linux is going to run, no matter what file system is going to be interfaced to those NAND drivers, for example. This means that they don't know what they have to do to guarantee fail safety. And equally, there's no clear specification from these file systems exactly what is required from the media drivers, so that somebody doing an integration process can make sure that the NAND flash driver matches the file system. As a consequence, my suspicion is that all these file systems are perfectly fail-safe when used properly. But the problem is that when you're doing system integration, people aren't understanding where the fault lines are and don't know how to fix these problems. If you're ever going to make a fail-safe system, you need to check that each interface does exactly what it's supposed to be doing. And that process is not happening. If you take a standard Linux distribution, load it onto a board support package provided by a company, how does anyone know that the NAND driver is developed to the standards required of the fail-safe file system under Linux? This is why it is so important to have a system-level approach to fail safety in file systems. So as I mentioned, Hcc have a very broad range of file systems for different scenarios. I'm going to avoid taking you through these. All the information about Hc's file systems is available on our website with our manuals and also several different comparison tables so you can see what the differences are between different file systems. This table is a very quick summary of the different use cases. Safe Flash is a fail-safe file system for NOR and NAND flash. Tiny is a very small optimized version of that for serial NOR flash. It takes advantage of the small sectors that you can erase in serial NOR flash. There's three variants of FAT file systems with standard media interfaces, and our Safe exFAT file system, which is an implementation of Microsoft's exFAT specification, which again can guarantee fail safety to different media. The one I would single out here is our smart metering file system, which isn't actually really a file system, but it makes a huge optimization. What it does is a lot of sort of data logging type, metering type applications, you're just writing data to databases. Normally, the normal way of approaching this problem is to open a file, your database file, and then seek to update a record, and then close that file and then keep on modifying it. This thing gets translated through the file system through several operations, maybe through a translation layer into several operations, or if it's an SD card, then internally that will become several operations, because an SD card is just a flash translation layer and NAND flash. And that becomes a lot of operations. By focusing on this particular application, we're able to create databases directly onto serial flash, skipping these layers of management and improving the access to the flash by maybe an order of magnitude in different use cases, which can reduce the cost and the wear on flash devices, which means if you're making a meter for long endurance or a data logger for long endurance, you can reduce the size of flash required, cutting cost. You can also model it very easily and have a much more focused solution for the purpose of doing data logging. And that's a very specialist application of a file system / database access method for managing flash that gets the very best in terms of cost and performance out of your flash device. Another big advantage of that particular system is it comes with modeling software so that you can actually run your use case in simulation on a PC before you go anywhere near your flash chip, and you can see how writing the records over a period of time will wear the flash, and you can then tune the size of the flash you need to use and the type of flash you need to use to get the best possible result. Excuse me. And the last topic I'd like to cover is the use of file systems in safety-based systems. So the terminology is slightly confusing because we call all our file systems safe because they're fail-safe, but there's safety-based developments in industrial 61508 type developments or aerospace DO178B type developments, where they want to use file systems in environments that are designed for safety. In these environments, we've done several projects. We have an ongoing one with a space shuttle. We had a previous one in an industrial control system. There's multiple of these projects based on different RTOSs designed for safety. And then the file system has to take a slightly different approach to a standard file system API. The aim here is to create freedom from interference between applications, partitions within that system. And to do that, we create non-blocking APIs for each of the API calls to the file system. To do that, we have a client-server operation where each partition or task has a separate client implementation that makes requests of the server that then does the file system operation. And this separates out the and then you have to, for each operation you do, you have to poll for completion, but that means that that partition can carry on running. Doing this, you can achieve complete space separation, meaning that there's no access between the different spaces of different tasks and partitions, so that there's a freedom from interference from that point of view. And there's a good level of time separation as always, but it's always complex because in the end, you're writing to a media which will block other accesses to the media. So the time separation has to be tempered by the fact that if you're dependent on getting data from the media, then other things could be accessing it. You've got to manage time extremely carefully. But from a high-level API point of view, you've got complete time separation because you're starting an operation and you can carry on doing other things while you poll for completion. So that's a way of addressing safety-based systems, for which Hcc is very happy to support when we're currently working with several safety-based RTOSs in this respect and are very interested in providing solutions based on this. So thank you very much for listening. I hope it's given you some food for thought. There's an enormous amount of information covered from a high level about different aspects of the file systems and flash management. If you would like to discuss a system project with a Hitex specialist, please contact Mike Muslik at this email address listed here, or for more information about the file systems, go to hcc-embedded.com and you complete comparison tables, user manuals, and supporting collateral. We're always very interested to work and discuss projects and your particular set of problems. As I hope I've shown, every application, every embedded system needs to be treated with its own respect, with its own detailed requirements, to be able to design a system with the suitable level of reliability you need to meet your customers' needs.